Now this first question is a one to do with intermolecular forces in the case of chlorine, and in sodium chloride to do with the ionic bonds in it. We're talking about the fusion enthalpy and the vaporization enthalpy. So it's important to know something about that before we get started. Now the enthalpy of fusion, going from a solid to a liquid, is really the amount of energy that we have to supply, we have to put in there to cause the molecules to start to move more and more vigorously until at last they can move and flow as a liquid, so some bonds are getting broken in that process. And as that's the case, it's going to be an endothermic process. And so going from solid to liquid is going to be endothermic. So all these energies would expect to be positive. Now if we're going from a liquid to a solid, the reverse of that, the enthalpy would be the same, except in this case it would be a exothermic process, and the enthalpy would be negative, so we just have to change the sign. Now with vaporization, that's going from a liquid to a gas, and so again we've got the same idea that we're going to need to put energy in there. It's going to cause the molecules to vibrate more, and eventually will break bonds, and this is an endothermic process. We're putting energy in there, so whatever value that is, it's going to be positive. And if we do the reverse process, if we go from a gas to a liquid, then energy is going to be released, and that's going to be exothermic, so we'd expect the sign for that to be negative. And those are some understanding of those values. Now this is for 1 mole of a substance, whether it be water or whatever it might be. In this case obviously it's chlorine and sodium chloride. And there's one more thing. Even though this question isn't asking it, sublimation, the enthalpy to do with that, is going from a solid to a gas. So that really is the same as adding together the enthalpy of fusion, so delta H fusion, plus the enthalpy of vaporization. So you should be able to logically work that out. Now when we look at chlorine, for example, we notice that this enthalpy amount is fairly low for fusion, and it's also fairly low for vaporization, and this is what we'd expect. As for chlorine, we have it's a non-polar molecule, and you should kind of make that statement, and the attractive forces involved are weak temporary dipole interactions. These are also sometimes known as dispersion forces or London's forces, and it really just reflects that it doesn't. So you need to talk about that in an answer. You should state that it's nonpolar. You need to state the kind of bonding and whether it's weak or strong. In this case it's weak, and how much energy it takes to break, not just in one phase but in both phases, going from solid to liquid and liquid to gas. So it takes only a small amount of energy. And in scholarship obviously you'd be writing these are the key points, but you'd be writing this out as full sentences explaining this. And going from solid to liquid and liquid to gas. So there's nothing terribly unusual about that. Now I'll talk about the bonding involved in sodium chloride. I mean, for a start, obviously this is a lot more energy than compared to chlorine, and obviously the significant thing is here, if we look at the vaporization one, is it's much bigger than the fusion enthalpy, and so we need to explain that. But first of all we'll just talk about the bonding, and in this case obviously we're talking about sodium chloride. It's got alternating sodium and chloride ions, and a 3D lattice, and it's held together by strong forces of electrostatic attraction. Now I'll try and give as complete answer as I can, and this is obviously what I'm discussing is ionic bonds which are very strong. So even to melt it, which is the fusion enthalpy going from a solid to a liquid, it takes a large amount of energy. So okay, so all I'd talk about is the amount of energy it takes to break up the lattice, because that's what's really happening when we're taking it from a solid to a liquid and putting in energy to do that. Now, there's a large difference in energy between these two enthalpies. In chlorine, they're fairly similar, and that kind of reflected the fact that the forces in chlorine were pretty similar in both cases. We're just, talking about intermolecular bonds, a temporary dipole-dipole bonding, and there's not a significant difference, but in the case of sodium chloride, it's huge. So this is what they're expecting us to talk about here. Why is that the case? Now, even if you're not sure, when you look at the data, it's telling you to go from a liquid to a gas. To separate these ions out takes a lot of energy. And obviously, you should be able to work out that must mean to separate ions takes a lot of energy. Whereas if you're just breaking up the lattice, the ions are still attracted to each other, but they're not really being pulled apart. Whereas going from a liquid to a gas, they're being pulled apart. So we need to talk about that. So you just need to talk about the fact that there is that difference, and that obviously it must take a lot of energy to do that. Well, the information is really telling you it takes a lot of energy. You just have to state the case when they become a gas. Now you're just really obviously breaking those electrostatic forces of attraction, those ionic bonds that exist.